Good evening. Our topic for tonight is integration by using trigonometric substitution. This is the last examples before we will go with the integration using partial fractions. So our topic for tonight, integration by using trigonometric substitution. Okay, eye contact, guys. Let's start. Integration by using trigonometric substitution. Second to the last example. The integral of dx over x squared plus 8x plus 17 equal to. Okay, the solution of this will be based on your knowledge of identities. So the topic is actually trigonometric substitution, so you should know something about identities. Okay, let's proceed with solution. Completing the squares first. The given denominator is actually x squared plus 8x plus 17. And we should transform this one to the form like an x squared plus a squared. That was our topic the last time around. The first one should be a perfect square and the second one should be a perfect square. And the given denominator is actually on the expanded form, so we don't know what will be the first quantity and the second quantity. But we could find for the perfect square of the first and the second. Completing the squares, we go back algebra. Ex squared plus bx plus c. Okay. This is similar to the given problem x squared plus 8x. Okay. I will put plus c over here because for the meantime we do not know the value of c, which will make the square term, the term with the x term, a perfect square. But we could do that. We could find for the value of c, because from algebra, the value of c is actually 1/2 of b over a, close bracket, quantity square. If you know the value of b and a, take 1/2 of that, then square it, that will be the value of c. That's from algebra, right? By inspection, the value of a is 1 over here. The value of b is the coefficient of x, b is actually 8. So if we try to follow this formula here, substitute the value of b and a, we could compute for the unknown value of c for the first term to be a perfect trinomial square. So actually c equal to 1/2, 8 over 1, close bracket, quantity square. 4 over 2 is 4, square that one, it will be 16. So it will be something like this. We can now rewrite this terms here as x squared plus 8x, okay, plus 16 minus 16, okay. We add 17 now, plus 17. The first 3 here is now a perfect trinomial square. And this is factorable to the quantity x plus 4, quantity square. So I place it here, x plus 4 quantity square minus 16 plus 17 is actually 1. Okay? What is 1? 1 is 1 square. So this is now of this form here. Okay? The sign is plus. Okay? And we got no radical sign. So this falls under the second and tangent. So the trigonometric substitution now, we will let x plus 4 quantity square equal to tangent square of theta. This is now our trigonometric substitution. Okay? Take the square root of both sides. Or raise both sides to the 1/2. 2 here cancel with this. Left hand side, x plus 4. 2 here cancel with this. It will now be just simply tangent of theta. Meaning x plus 4 is tangent of theta. Take the differential of both sides. Why we take the differential of both sides? We need the value of the x in terms of the trigonometric substitution. So we will compute for dx. Dx, the differential of x is dx, the differential of 4 is 0, equal to the differential of tangent of theta is secant square of theta, differential theta. So this is now 0. So dx is secant square of theta. We need this relation here to solve the problem because we got a dx in the given problem, right? Excuse me. Okay? Substituting. That's why our solution is trigonometric substitution. Substituting. Okay, guys? Eye contact, guys. Therefore, the integral of dx over x squared plus 8x plus 17 equal to the integral. What is dx? Dx is this. Secant square of theta, differential theta. All over the equivalent of the denominator. The equivalent of the denominator will be tangent square of theta plus 1. Why tangent square of theta? This is factorable to x plus 4 quantity square, right? And that is tangent square of theta. So we replace the first the term x plus 4 quantity square by tangent square of theta. So that's now tangent square of theta. Okay, plus 1. Right? You got it? It's easy. Okay. But 1 plus tangent square of theta, identities. Recall your identities. That is secant square of theta, right? So the resulting integral will be the integral. I just rewrite secant square of theta differential theta all over the equivalent of 1 plus tangent square of theta is secant square of theta, right? Trigonometric identities. This one cancel with this. So actually what will remain on the right hand side will just be the integral of the differential of theta. It is this. The integral of the differential of theta. When the integral goes this near the differential side, they will try to cancel out each other. So the right hand side will just be simply theta plus c. Okay, let's try to bring out the final answer in terms of x. But what is theta? Oh, theta is it's like this. You go back to the substitution, okay? You go back to the substitution. Our substitution is x plus 4 equal to tangent of theta. Right? To solve for theta, take the arctangent of both sides. Okay? The arctangent of x plus 4 is arctangent of x plus 4. Okay? I place it on the right. And the arctangent of tangent of theta is just theta. So this is the equivalent of theta in terms of x. So our final answer is just arctangent of x plus 4 plus c. It's all identities. Okay guys, you got it? Okay, let's bring out the last example. Last example will be the integral of dx over the square root of a to the 2x minus 1 equal to. A to the 2x minus 1 is under the radical sign. Okay? We are just unlucky for tonight. The term inside is in terms of exponential function. So, but don't be afraid with exponential function. We know exponential function. Okay? Our trigonometric substitution will be something like this. We will let e to the 2x equal to secant square of theta. Okay? I use this because I was thinking of an identity related to secant square of theta. Because this is minus 1, I will let this secant square of theta. Okay? Take the natural logarithm of both sides. Because we will compute for the value of x. Okay? That's our representation, right? Then take the natural log of both sides. Okay? If we take the natural log of the left-hand side, okay, loss of exponent. We bring down the exponent times the natural logarithm of a. Okay? Actually, the right-hand side is actually secant of theta quantity square. Okay? So actually, we could also bring down 2, then take the natural logarithm of this, 2 natural logarithm of secant of theta. Okay? These 2 here cancel with this. Okay? The natural logarithm of a is 1. Okay? Use your calculators. What will remain on the right-hand side, left-hand side rather, x. Okay? Equal to, this 2 is gone, so what remains on the right-hand side is natural logarithm of secant of theta. You can put a quantity there. Okay? We need this relation here because we needed this one to compute for the x. And to compute for the x, we are now given x as a function of theta, so take the differential of both sides. The differential of x is dx. The differential of the right-hand side, it falls under the natural logarithm. Okay? Differential calculus. 1 over u times du, where the value of u for the meantime is secant of theta, right? So this is 1 over u times du. 1 over secant of theta, the differential or derivative of secant of theta is secant of theta, tangent of theta, differential theta. And luckily, this secant of theta cancel with this. So dx now equal to 1 times tangent of theta is tangent of theta, differential theta. This is the relation of dx as a function of the trigonometric relation. Okay? Okay, let's solve the problem now. Let's do this one first. Let's compute for the value of e to the 2x minus 1. E to the 2x minus 1 equal to, what is e to the 2x? It is secant square of theta, right? It is this. So this should be secant square of theta minus 1. Okay? But 1 plus tangent square of theta equal to secant square of theta. Right? If we put this on the right, this will be minus 1. This is gone, right? So tangent square of theta is secant square of theta minus 1. So we could replace this one by the value tangent square of theta. Okay? Let's go back now to the original problem. Therefore, the integral of dx over the square root of e to the 2x minus 1 equal to the integral. What is dx? Dx is tangent of theta, differential theta. This is. Okay? All over the square root of a to the 2x minus 1 is actually tangent square of theta. So, this will be the square root of tangent square of theta. Luckily, tangent square of theta is a perfect square. We will take the square root, so the square root will just be simply tangent of theta. The resulting integral will be the integral tangent theta differential theta. The equivalent of the square root of tangent square of theta is just tangent of theta. And again, luckily, this tangent of theta cancel with this. Okay? Right hand side that remains is just the integral of differential of theta. If the integral goes near this differential sign, they will try to cancel out each other. Right? So the right hand side will just be simply theta plus c. Okay, let's try to bring out the answer in terms of x. How could we do that? We know that e to the 2x is secant square of theta, right? I will put it here. You might not see it, it's too low. We know that e to the 2x equal to secant square of theta. We solve for theta, okay? So take the square root of both sides, right? So this should be e to the 2x, raise that again to the 1/2 equal to secant of theta quantity square, raise that again to the 1/2, right? We take the square root of both sides. These two here cancel with this. What will remain on the left hand side will be e to the x. It is now just simply x equal to, these two here cancel with this. What remains on the right hand side will be secant of theta. Then to compute for theta, take the arc secant of both sides. Okay? The arc secant, okay, of e to the x equal to the arc secant of e to the x. Okay? The arc secant of secant of theta will be theta. So this is the value of theta in terms of x. Okay? So our final answer is actually arc secant of e to the x plus c. That's it. Can you see it, guys? It's too low. The final answer will be arc secant of e to the x plus c. That's our final answer. Okay, guys, that's it. It's easy. Okay? Final answer, arc secant of e to the x plus c. Because the right hand side is just theta plus c, but we need to bring out the answer in terms of x. But we know that theta is arc secant of e to the x. So the final answer will be arc secant of e to the x plus c. Okay, that's it. This will be the last part of the integration by using trigonometric substitution. My next topic will be integration by using partial fraction. Good evening, Los Angeles.